All right, in this lecture, we are going to increase the level of complexity again. That's kind of the phase, the pattern here, right? We're just doing ice tables and ice tables and ice tables, and we're looking at slightly harder examples each time. So this one, this is such a great reaction. It's splitting water. It's what plants do to create oxygen. It's a beautiful thing. It's photosynthesis. So you're given a equilibrium concentration, you're given a chemical reaction that's balanced, and you are given a concentration of your initial reactants. Um, Perfect, right? And so this is what all of these equilibrium problems are going to look like. This is the style of information you're going to have for most of them. Like some of them will come at this from a different angle, but so let's go ahead and just try to solve this problem. And typically I have students do this in the classroom rather than online. And so if you want to try this on your own first, I would strongly recommend it. But I will give you a little asterisk sign to this. Give it a try. Give it a try until you get frustrated. And when you get frustrated, then finish watching this video, unpause, and just like, but find that point. Find that point where you're like, oh gosh, wait, really? Now what do I do? That's the point that I want to get at, that frustration moment. It's a learning moment, I promise. So pause. All right, now I'll continue. So I'm going to write out my expression and I'm going to write out my equation. So my equilibrium constant is this 7.3 times 10 to the negative 18th. This reaction doesn't happen very well unless it is catalyzed by something like photosystem 2. So it's going to be the concentration of hydrogen and it's squared because I have that coefficient of 2. And then it's times the concentration of oxygen, all divided by the concentration of water, also squared. And now I'm including water because it is in the gas phase. And so everything is in the gas phase, which means water's not the solvent. Water is part of this reaction and it'll impact equilibrium. So we include it. And it has a coefficient of 2. That's why it's squared. All right, so I got that piece down. I'm going to create my ice table. So I have my ice table constructed. I'm going to input my initial concentrations now. I have an initial concentration of water 0.1 molar. So we can assume we have 0 for our hydrogen and 0 for our oxygen since it's the beginning of the reaction. And now we need to know our equilibrium concentrations. So I'll go through and work through my change row now. So water has a coefficient of 2, and we know this reaction is going to proceed towards products because I have none of them. So my Q is going to be equal to 0, which will be less than that extremely small K value, but it's still less than that K value. So I'm going to subtract 2x from my water and my reactant side. I'm going to add 2x for my hydrogen and add x for my oxygen. It's really easy to forget to include the 2 from our coefficients in the change row. So I'm just pointing it out. It's something I still forget to do sometimes. It's just easy to do. And now I'll write out what my equilibrium concentrations will be. I'll have 0.1 minus 2x. I'll have 2x and I'll have x. All right. So this is pretty standard so far. So now I'm going to go plug these into my equilibrium expression. So I've got this 7.3 times 10 to the negative 18th, absurdly small, is going to be equal to that hydrogen concentration first. So that's 2x. And it's squared. And that is times x, which is not squared. It's just to the power of 1. All divided by my water concentration, which will be 0.100 minus 2x squared. Okay, now it's time to start trying to get everything on one side or get this to a point where I can reduce it down to just x equals something and isolate x. So doing that, I'm going to start playing around. I'm going to first expand out my bottom using foil. And so I'm going to get something that looks like this. So again, trying to set this up so I can use a quadratic or something similar. I've got 0. I'm going to get everything onto one side of the equation and set it equal to 0. And I end up with something that's not ready for a quadratic. So I get this beast. It's 0 is equal to 4x cubed minus 2.92 times 10 to the negative 17th x squared plus 2.92 times 10 to the negative 18th x minus 7.3 times 10 to the negative 20th. Blah. That's a lot. And that is not a quadratic at all. That is a cubic. We need to be able to solve that 4x cubed. That makes all the difference in the world. That takes us from being, yeah, you just plug it into the quadratic to being annoying. So this is a cubic. And I'm not going to tell you to solve it at this point. Instead, I'm going to teach you an approximation that is going to save you from having to solve cubic equations for x right now. I mean, you can do that, and it's great practice if you're doing that in the math classes you're in right now. Please go for it. But we're not going to expect you to do that in our class. Instead, we're going to teach you about approximations in ice tables. So in general, if, this is the big if the equilibrium problem is complicated to solve, you're like, ugh, and there's a big and here. I should put and K is small or very different, then we can ignore the change in the initial concentration. That's right, because if K is really small, that means we're not going to form a lot of our products, right? Now, we still need to know how much we're going to form, especially when we're working from zero. But it means that whatever change is going to occur from our initial concentration will be so small that it'll actually be a rounding error. Like we won't have enough significant figures to actually track that change. And so if we're going to just be rounding anyway, let's just round away that X now before we try solving this and save ourselves the hassle of solving a cubic equation, right? So this is only going to work because the change in X is going to be so small that we can ignore it. That's the only reason. That's the only time you can do this approximation. Now, you are going to be staring at problems a lot going like, can I approximate? Can I approximate? Can I approximate? And you're going to want to do it all the time. So you're only going to do it if, I'm gonna actually change this very much. Like the bare minimum is that initial concentration you have that you start with needs to be significantly larger than 100 times the equilibrium constant. So for example, if I have an initial concentration of my reactant, and let's call it, and it's equal to 0.1 molar. If my K is equal to 0.015, I'm not going to be able to do the approximation. Because 100 times my K value would equal 1.5, right? And that is not much smaller than my 0.1 molar. So no approximation. And that's a bit of an exaggerated one. That one should be hopefully obvious. If instead I have something where I have my concentration of my reactant is still equal to 0.1 molar, and my K value is equal to 1.5 times 10 to the negative 6. Now we're talking, because this K value, 100 times K, is going to be equal to 1.5 times 10 to the negative 4th. That's a small number. That is, I would argue, significantly smaller than our concentration. So I would say that 0.00015 is significantly smaller than 0.1. And so I would say our approximation is okay. So what would we do? Let's pick up where we left off, frustrated with our water splitting problem. So here we were. This is exactly where we got upset, right? We had a quadratic. So what we're going to do in our ice table is we're going to say, well, you know, this is 10 to the negative 18th is crazy tiny, especially compared to 0.1, which is small, but it's not that small. So what we can do is we can say, all right, well, we're going to assume this is insignificant. And when we do that, then we can assume that equilibrium concentration is actually still just 0.1. And so that simplifies this term up here. That makes this right here simplify into just 0.1 squared. which is a lot easier to deal with. Then our equilibrium expression is something that is more manageable algebraically. It's now going to simplify into something where we can just take the cube root of an expression rather than solve a cubic equation. And so we're going to end up with our X expression when we just make that one change to our reactant. We're going to be able to simplify this to something we can take the cube root of. And it's going to give us 2.6 times 10 to the negative 7th. And we can double check, is our approximation appropriate? Well, if I take my 0.1 and I treat that, plug that value in as X, I get 0.099999. It's going to round to 0.1 with the number of sig figs that we have. And so our approximation was reasonable. So that means that we can then calculate using that X, the concentration of our hydrogen and our oxygen. We're going to get for our hydrogen 5.2 times 10 to the negative 7th. Which is, significant because that's larger than 0, and we now know the amount. And it was a much more simplified problem.